Hi, how are you? So we're coming to another question in our series about the solving for the relative velocity, relative acceleration equation. And in this example, we have the pulley is being connected at the block B at the point A. Okay, so we're talking about the point, which is going to be, just give me the laser or the pen. Anyway, yeah. So we're talking about the point A here, the one in the middle, and this will connect this wheel to that block. So what's happening is that at the code CF from here, the point C to point F, if this one is going to be actually unwind from the inner hub with the motion shown, the code DR is going to be unwind from the outer rim. Um, Now determine the angular acceleration of the pulley at the instant shown. So we need to find the alpha of that pulley. The solution should be first done by defining that there is no slipping at the point D uh, between the outer rim and the core DE. Now, take a look to this scenario. We're going to consider something similar to the car wheel, or one of the questions that are available on the book about we have the rim, we have two of them, we have this one to be connected to that, and it's moving on the floor. So the floor not moving, that means we're going to have that the IC is going to be here for the two velocities. So that will be the scenario. So we can say that there's no slipping between the outer rim and the core DE because this rope, it doesn't move. It's just simply getting out of the rim. So in that case, the velocity of the core DE is going to be equal to 0. It's not moving. And in that case, the VD in the outer rim is going to be equal to 0. And then the point D is the IC of the system. Now that's good. Now if I get to know what the velocity here, I can calculate the omega of the ring because I can find what the value of the RC to D, and I can find the omega of the wheel by using the velocity at the point C. So we are going to have the kinematic diagram. Well, actually, I just wrote the previous one and I made it more clear. So what we have here, this will be the x direction, and to that direction is going to be the x. This one is going to be the y, and toward us is going to be the z. So the omega and the alpha is going to be around the z, having the k value, and everything else like the velocity c and the acceleration c is going to be on the j direction, negative, because it's going to go downward. The same thing for the velocity of the block or the velocity of the point A, which is going to be negative because it's going to go downward. So from there, we're going to start to do our analysis. We try to find the acceleration at the point D. The acceleration vertical is going to be 0, but the horizontal one is going to have the normal velocity at that point. So the known values are going to be the acceleration at the point C in the y direction is given as -4, and the velocity at this point is going to be -3 meters per second. The unknowns are the omega and the alpha. We assume that in the vector acceleration process. So the first solution is going to be writing down the acceleration equation for the AD with relative to the AC and to find the omega and the alpha. So the equation is going to be as following. The AC relative to the AD is going to be AC equal to the AD, both as vectors, plus the alpha multiplied by the RCD, this in between the C and the D, minus the omega square multiplied by the RC to D. Now remember something that the omega is unknown now and the alpha is unknown, but anyway, we can know what the AC is because it's going to be and the x direction is unknown and the y direction is going to be equal to -4. For the AD, we know it's going to be in the y direction equal to 0, but we don't know what its value till now for the x direction, but obviously it's going to be the normal velocity of the point D. If I know what the value of the omega of the wheel, I can find this acceleration. And for the omega and the alpha is unknown, and we're going to use find the value for the omega by using the velocity analysis. So yep, that will be the ADX, which is a normal acceleration of the point D, omega square multiplied by the RA/D. So this is not X, that's multiply. Now we are going to do the solution number 2, which is going to be find the relative equation between the acceleration A and the acceleration C, and after that we are going to find the relative acceleration of D with relative to the acceleration of A. So the first one is going to be that one, the same one we had before. I'm talking about that equation. So the AC is going to have two components. One of them is unknown, which is the I component. The other one is minus 4J. For that one, the I component is 0. The J component is going to be omega squared multiplied by the RAD. The alpha is unknown, multiplied by the distance between C and D, which we know that's the C, that's the D. Okay, we can have it as a vector, so it's going to be just the value of that. In the y direction is going to be 0. In the I direction is going to be equal to 25 plus 50 millimeter divided by 1000, and that's make it 0.075 meters. Then we said that by using the velocity analysis, we can find the value for the omega. We can square it, and then we are going to multiply it by the 0.075 I. Now, after we're going to find that, if I going to know what the AY is, then I can write down the relative acceleration equation for the A with relative to D. Okay, and then I can solve for the value of the alpha or the value of the omega. So now we can use either, but we're going to use the one that have more knowns. So we start first to find the value for the omega. If I said that this will be the IC, and this velocity is perpendicular to it, so I can say that the VC is equal to the omega multiplied by the distance from C to D, which is 0.075 meters. So in that case, if I know what the velocity is, I will divide it by the distance, and this will give me the omega. So you can find that to determine the omega, I'm going to use the velocity analysis. The distance from C to the IC is going to be equal to, from the A to the point D is 0.05 millimeters, and the distance from C to A is 0.025 meters, and then the total is going to be 0.075. Now the omega is going to be equal to velocity C divided by that distance. So we'll come to 40 radian per second. Okay, so now we found that. Now I can find the velocity at A. It's going to be very simple right now, because now around the same instantaneous center, with this omega now is known, the velocity at A is going to be equal to the omega multiplied by the distance from the point A to the point D, which is 0.05. So I can do the basic calculation, and I will get that the velocity at A is equal to 2 meters per second, and this will be the velocity of the point A and the velocity of the block going down at this distance. Now we continue with the work, and I'm going to choose the first equation, which is going to give me a relative acceleration between the point C and the point point D. So that's the equation. Once again, this is not x, this is multiplication sign. And now let's come to this equation. I know the the y direction of that, but not the x direction. So I'm going to write it down as the acceleration cx plus the acceleration cy, I and j, of course. For the AD, we said that one of them is going to be 0, which is the vertical, but the horizontal is going to be equal to the omega square multiplied by the distance of the CIC, and then we're going to have minus the omega square multiplied by the RC to D. Okay, so now we know this value here is going to be just in the x direction, and it's equal to 0.075. So now that will be the equation we're going to write down. Take all the components to be vectors, and this will be scalar multiplied by the vector. We know the value now for the omega, so we can actually start to do the analysis. Here, this one is known. For this one is 0. This one is known for the RCD, and the omega is known. The alpha is unknown, and the ACX is unknown. And for this one is going to be equal to the omega square multiplied by the R D to X, D to C, sorry. So we can simply write down this one. Okay, so that's what we're going to use. We are going to multiply whatever by the whatever, and we are going to come to the equation that has the alpha and the dx to be the unknowns. So we're going to just keep doing that now. Okay, so we said that this one is equal to 0. We know that. Okay, and we're going to have this one is unknown, this one is unknown, and the alpha is unknown. So we start with the I first. I'm going to have the ACX to the left is going to be equal to the ADX plus 40 square multiplied by 0.075. And for the J's, we are going to have minus 4 is equal to the ADY minus 0.075. Now we can simply solve for this equation, and we can find the value for the ADX. So the ADX is going to be equal to omega square multiplied by the RAD. We should have negative at the beginning. So the ADX is going to be equal to minus 80 meters per second. Now, if I get to put in this equation, this one is going to be now known. And I can find this one. For this part, we know this one is 0. So we're going to have that the alpha is equal to minus 4 divided by 0.075. Okay, and from the equation 1, we are going to find that the ACX is equal to 40 meters per second square, and the alpha is going to be equal to 53.3 radian per second square. Okay, so that's it for this question, and we are going to have only one question to go with.